Hello to all viewers. Thank you very much for your participate and sorry. Do you have my voice, dear students? Okay. Okay. Thank you very much. Thank you. Let me begin this session. In this session, we see the definition of continuous function on topological space. Let x and tau x and y and tau y be two topological spaces, and let f from x to y be a function. We call f is continuous at x0 if the following holds: if n belongs to the set of neighborhood of f of x0, then the inverse image of n belongs to the set of neighborhood in x0. Please note that for each sorry. Okay. I recall that okay. I have a problem with this board. Okay. In a topological space x and tau, for example, if x belongs to x, n is an element of neighborhood of x0 whenever there exists an open set, an element of tau such that x0 belongs to u and u be a subset of n. Okay, so that n of x0 equal to the set of subsets of x such that for a for an element of 2 or for an open set such as U, we have this property. Okay, in the definition of continuous function, a function f from x to y is called continuous at x0 whenever we have this property. Okay, f from x by its topology to y by its topology is continuous at x0 if and only if we have this property if n belong to neighborhood of fx0, then the inverse image of n be an element of neighborhood of x0. Okay, and this is this definition in this line. Okay, and we have a very useful proposition: let x and y be topological spaces and f from x to y be a function. Okay, then the following three statements are equivalent. 1. F from x to y is continuous on x. Continuous on x is mean that f is continuous at all points on x. Okay, this is the definition of continuity at one point. And in a statement 1, we say f from x to y is continuous on x, on all points in x. Okay, this statement equal to this: for each open subset of y such as U, the inverse image of U is open in x, and this equivalent to this sentences or a statement: for each closed set F of y, the inverse image of F is closed in x. And this is very important in topological spaces. Okay, let I write this again for you. Okay, proposition: let x and y are topological spaces, then the following statements are equivalent. One, two, and three. One, t from x, t or f, for example, I use the symbol similar to the book, is continuous. Continuous on whole of x. 2, if u belong to y, then the inverse image of u belong to x, or equivalently, if u is an open set of y, then the inverse image of u is an open subset of x. And 3, if f is a closed subset of y, then the inverse image of f is a closed subset of x, or equivalently, if 1 minus f belong to two of y, then x minus the inverse image of f belong to 2x, okay? Because we know that if the complement of f is open, then f is closed. These two statements are equivalent, okay? Closed. F is closed if and only if y minus f is open or belong to our topology, and the inverse image of f is closed if and only if its complement is open. And also this statement, u belong to index y equal to u is an open subset of y, and this equal to this statement, the inverse image of u is an open subset of x. But these three properties are equivalent, and its proof is easy and important. Okay, dear students, Do you have my voice and image? There is no any problem. Do you have my voice and image? Okay. Okay. Thank you very much. For example, if we want proof one implies two, we must assume that f is continuous on all points in X. So that for each X in X we have this property. If n belongs to n indexed by f of x, then this inverse image must belong to the set of neighborhood of x. Okay, we have this property on all x in x. Okay, and we must prove this property, so that we must assume that U is open and must prove this inverse image is an element of this topology. Okay, let's U be an open subset of Y, then for each X in the inverse image of F under U, we have F of X is an element of U by the definition of inverse image. Okay, but if is continuous at X, okay, because we assume the statement 1, so that f is continuous in all points on X. Okay, so that f is continuous at this point X. So that since U is an element of n of fx0, we have the inverse image of U is an element of fx0. We use this definition. Okay, for each n in this neighborhoods, the inverse image must be an element of this neighborhoods. Okay, and it is easy that U is an neighborhood of f of x0 because this is an open set and contains fx0. Please note that. This holds because so that fx, not fx0, fx is an element of U and U is a subset of U, okay? U is an open set, so that this U must be belong to n of fx. This is fx, okay? Because we said x belong to this set, okay? And so that there exists an open set, for example U x, such that x belong to ux and ux is a subset of this inverse image. By the definition of neighborhood, okay? Any element of this set or any neighborhood of x0 have this property, that exists an open set by this property, okay? Now since this is a set in neighborhoods of x, we must have an open set by this property. This implies that f of u the inverse image of f, the inverse image of u under f equal to this union all ux x belong to this set, and this is obvious because by this process for each x we found an open set. Please note that for each x in this set we found an open set such that x is in ux and ux is a subset of this set, okay? We prove this statement, please note, okay? And this implies this equality because all ux is a subset of this set, so that this union must be a subset of this set. all ux is a subset of this, so that this union is a subset of this inverse image. And conversely, each x in this set belong to one of these open sets. Each x in f minus u is an element of ux, so that belong to this union. And so we have this equality, and this equality implies that this set is open, because we know that any union of open sets are open. Okay, this implies that this set is open set, is an open set, because this set is a union of open sets. Okay, we said in the previous sessions that any union of open sets are open sets. Okay, so that since all ux are open, this union is open, or this is an open set, so that we prove the statement 2. If u is open set, the inverse image of u is an open set 2. Similarly, we can prove the inverse of this statement. Two implies one. Okay, let's two holes and two holes and we want to prove 1 n and x is an arbitrary element in x. We prove that, or we must prove that f is continuous at x. If we prove this, since x is arbitrary, f is continuous on whole of x. Okay, continuous on whole of x. For this, let's n be an element of this, or n be a neighborhood of f of x. Okay, then there exists an open set such as U by this property: f of x belong to U and U is a subset of N, because N is a neighborhood of f of x. Okay, now by 2, the inverse image of U is an open set or open subset of X. This is our assumption. Okay, 2. Any inverse image of open sets are open sets, because we assume that U is open, so that by 2 this inverse image must be open, and this is an open subset of X. Okay, open subset of X. Okay, since X is an element of f minus U and f minus U is a subset of f minus N, by this U is a subset of N, so that we have this inclusion. Okay, and this is an open set by assumption 2. This set is a neighborhood, of X, so that we prove that for any neighborhood of N of f of X, the inverse image of N is a neighborhood of X. Or briefly, we prove that if N is an element of this, then this inverse image is an element of this set, and this implies that F is continuous on X. Okay, so that we prove that 1 implies 2 and 2 implies 1, and easily we can prove that 2 and 3 are equivalent, because if we assume to behold for 3, please see statement 2 and 3. The inverse image of every open set are open, the inverse image of each closed set are closed. We assume that the inverse image of any open sets are open sets, and we must prove that if F is a closed subset of Y, the inverse image of F is a closed subset of X. Okay? Let 2 be wholes and F is a closed subset of Y, then Y minus F is an open subset of Y, so that by our assumption 2, the inverse image of this open set is open subset of X. But the inverse image of this set equal to this inverse image minus this inverse image, and this is equal to X, so that this is X minus, so that this open equal to this set is open. This set is open, so that this is a closed set. Okay? So X minus F minus F is open, or equivalently F minus F is closed. And similarly, we can prove that 3 implies 2. This is similar to this. You must only change closed by open. Okay? Okay? 3 implies 2. So that we have this important proposition and this is very, very important because, for example, if we consider two sets X and Y, okay? X and Y, and also consider a function, for example, f from X to Y. Okay? A function from X to Y. For example, this function. Okay. Okay. Now this function is continuous on whole of x, okay? Whenever for any open subset of y such as u, the inverse image for example this inverse image, okay, f minus u of u under f is an open subset of x. This is inverse image, okay, because you know that inverse image of u is the set of all x in x such that f of x belongs to u, okay. For any subset of y such as u, the inverse image of u is a subset of x. This function f is continuous on whole of x. This function f, okay. Any open subset of y have an inverse image, open inverse image in x, okay. Any open subset have an inverse image that is open in x, and this is a very important proposition. If it continues on x, if and only if f minus u is open in x for all open subset u in y, and f minus f is closed in x for all closed subset f of y, okay. Are you know this proof, dear students? Are you know? Please, I use Google Translate. هل لاحظت الدليل؟ okay. Yes or no? Okay, thank you very much. Thank you. And we have a very easy proposition. Let x and 2 and y and 2 and z and 2, 2x, 2y, 2z be topological spaces such that g from x to y is continuous at x0 and f from y to z is continuous at g of x0. Then this composition function f of g is continuous at x0, and its proof is very trivial. We must prove that g of f is continuous at x0. Please note that we have two functions. One function is f from x, f from y to z, and one function g from x to y, so that we have this composition function FOG. So that FOG is a function from x to z. If we want to prove that this function is continuous at x0, we must consider an open subset of z that contains x0. Please note that. We must consider an open subset of g of xf in z, okay? More partially, we must begin by this element, and this is a brief space. Please note that x, y, z, we have this diagram, x, y, z, and this is our f, this is our function g, and this is the function f o g, okay? If we want that f o g is continuous on x0, we must prove that for each m, for example, in n of FOG x0, FOG minus m is an element of n of x0. We must prove this statement. For this, let's m belong to n of FOG x0 or f of g of x0, okay? Then since f is continuous by our assumption, because f is continuous on g of x0. This is our assumption, okay? F is continuous at g of x0. So that by our assumption, the inverse image M must be belong to N of G x0, because F is counted at this point. Now, since G is continuous at x0, this is another assumption, okay? G is continuous at x0, so that the inverse image of this set under G must be a neighborhood, the inverse image of this set, okay? The inverse image of this set F minus n must be belong to N of x0, but this is equal to F of G minus n. This process shows that for each m, for each neighborhood of this point, the inverse image of m under this function is a neighborhood of x0, and this implies that f of G is continuous at x0, okay? And we prove this statement for each m, F of G minus m belong to this. And this equality prove easily that these two sets are equal, because if you consider, for example, x from this set, by the definition of inverse image, f of G of x must be belong to M, so that f of G of x must be belong to M, so that G of x must be belong to the inverse image of M. If you consider this as an element such as y, okay, f of y is an element of M, so that y must be belong to, you know this, f of y is an element of M, it is equal to y must be belong to the inverse image of M, and we write this y belong to this set if and only if f of y belong to M, okay? And also we know that an element x, for example, is an element of f minus n, for example, if and only if f of x belong to n. In this situation, we see that g of x belongs to this n, so that x must be belong to the inverse image of n. This is all n, okay? F, this is all n. We must change this to g, because we use g in this, okay? G inverse, g of x belong to n. This is your n, okay? G of x belong to n, g of x belong to n, so that x must be belong to the inverse image of n under g. This is all n, okay? And similarly, we can prove the inverse of these implications, so that these two sets are equal. These two sets are equal. Okay, in the following, we define a net in topological spaces, okay? Before this, we have this definition. A relation, for example, this relation on a set is an ordering when the following three requirements are satisfied. We refer to such sets as ordered sets. These three properties, for each alpha in X, alpha has this relation with alpha. We say that this relation is reflexive, okay? 2, if we have these two relations, alpha, beta and beta, gamma, then alpha has relation with gamma. And this is transitive property. And antisymmetric properties. If alpha has this relation with beta and beta with alpha, then alpha must be equal to beta. So that this relation must be reflexive, transitive and anti-symmetric. Then this relation is called an ordering, and this set is an ordered set. Definition: an ordered set X is called directed when for each alpha and beta in X there exists n gamma in X with these two properties. Alpha has this relation with gamma and beta has this relation with gamma, so that this ordered set is called directed, okay? For example, in R, ordinary relation in real numbers have these properties, okay? example. This is a very easy example, okay? Real numbers and ordinary relation. It is very easy that ordinary relation in real numbers have all of these properties. Okay, I must go to a work and we can continue these topics in the next session. In the next session, we define the definition of nets, okay, and convergence of nets in topological spaces. I see this in the next session, inshallah. Do you have any questions, dear students? Do you have any questions? Okay, thank you very much. Thank you for your attention and goodbye for now.